Okay, so ladies and gentlemen, let's continue with the last part for today, the last model. If you open it, you should see this circle-like polygon filled with these streets. So the idea of the last exercise is to introduce a few new things concerning the generation of geometries, for example, a street network, and repeating the parts for linking the network analysis that Sven introduced you last week to the simulation model. So this was something you have seen last semester already. And then it's linked as well to another generative part where we can generate parcels and buildings automatically. That's similar to what Malik has shown you partially, plus some additional buildings where we provided some components, but they offer you less control compared to what Malik introduced, but they are already finished components. Because I placed it where we have had the old example file of Weimar, what you need to do to see it is to activate the viewport, the top viewport. Click on the network smooth component, for example, and right-click somewhere on the canvas and select zoom, and then you should see this circle. A new component coming from this decoding spaces toolbox collection. If you press this Alt-GR and left mouse button, you see from where the component comes from. And this is this one, the street network synthesis. That's the This generates you automatically a street network based on certain control parameters. We can do this also with a new network, just to explain you the main idea. If I turn this off and if you place a new one, and if you zoom again into the output, then this is somehow the predefined test geometry that's generated. And you can link this to some primarily or some initial geometries. The bounding geometry and the initial streets are the most important ones. So let's try to do this similar as we've seen it in before. If we want to make a border, we need where is it? This polygon. So you cannot use a circle because a circle is not a polyline. We need this kind of polygon that you can draw. And you can define the number of elements, but you can also draw a free polygon with some defined shape, doesn't matter. You can use whatever you want. And we want to have some initial segments that links our newly generated street network to the environment. Can draw something like this. You can also draw a line inside. Just take care that these are lines, respectively polyline curves. And to use it now, we can use this geometry components and set on geometry for the first one. So right click on this geometry component, set on geometry and select one of them. And then we can link it to the boundary. And then you see the network is generated inside this polygon. And now we need our initial street segments that we've created. Therefore, right click on this component and set multiple geometries. And then you can select the line segments, pressing Shift, and select 4 or 5 or 2 of these components, enter, or right mouse click. Oh. Yeah. Sorry, once again. Okay, then the 4 or however how many you selected should be marked green if you select this component, and you can link them to the initial street segments, and then you see your street network starts from these lines, respectively integrates them. And if you move them, the network is adapting. There are a few control parameters. One is the seed, the seed for randomness, or seed for the random generator. If you want to generate always the same network, you need to define one number. If you change it, you just generate different random numbers, but if you go back, you can generate the same network again. And this tree depth, this controls the size of the network, so how many steps you grow from the initial segments. If you reduce this to 0, then you see nothing is grown. If you say 1, then it grows 1 step from the points that are inside the polygon and coming from the initial line segments. If you say 2 and 3 and 4 and 5, then it fills the area. You just have to take care that you don't use too large numbers. So I think at 15 steps it doesn't work. So if you restrict it to 10 for the smaller cities, it should be fine. What you can control as well is, for example, the random angle that you see. If you reduce it, for example, if you don't want to have random angles to 0, then it tries to continue with these lines in a kind of a grid. But there are still some irregularities that appear because these lines, they try to snap to existing lines and not to create some weird small spaces. And therefore, it never creates some perfect grid if you start with such kind of random geometry here. This min-dist parameter controls the distance. If you have two vertices, two nodes in a certain distance to each other, you can define until when they snap together to form one node. So if I increase this, you see it's cleaned because they snap. And if you lower it, you see it's you have less of these adaptation errors destroying your kind of rectangle or rectangular grid. And if you increase it, you have more and more of these different lines. You can also control the maximum length of an new generated street segment and the minimum length. So you can add here parameters or just adapt it here. And so the algorithm generates a new segment in this range, in this between, at the moment, a segment in the length between 30 and 100 meters. And this is added, so if you don't want to have this randomness, you can put them close to each other or take the same values here. Max arms controls the maximum numbers of arms of streets that connects to a crossroad, which is usually fulfilled only in the cases when this min-dist parameter forces a snapping. Then you may also end with more arms, but usually you don't have more than this. At the moment, 4 arms are defined. The outer boundary, that's important for later, because at the moment the outer boundary is a street that you defined here. But in the case that you say, okay, this is just a boundary where I want to restrict the network to grow further, but this shouldn't be a street. You can have the same boundary or a smaller one that restricts the growth of the network, but without being a street, which is important later if we generate the parcels. We apply the rule that every parcel needs to be connected to a street, and if this is not a street, then the pattern looks different than if it is a street. Okay, the only thing that I've added after the generation of the network is this remove stubs, which removes, you see here, these are line segments that are not connected to another line, so they end here, so-called stubs. And if we want to remove them, because we don't need these dead-end streets, we can use this C# script. So that's nothing special, you can look into it. Basically, we have here the for loop, let me zoom in, that goes through all lines, and you compare all the ends of the other lines if they have a connection. And if both ends of a line have a connection, then you say, okay, it's connected, it's not a stub, that's connected A or connected B. And if both are true, you know it's inside of the network, both sides are connected. If only one is connected, then you know it's a stub that you want to remove. And you return the list of lines that remains if you remove these stubs. So I think this stuff you should be familiar with. This is just lists and testing lines. And if you have the same point from 2 lines at the same place. And the last step is just for cleaning. This network smooth component comes also from this decoding spaces toolkit. Usually it doesn't have an effect, but sometimes it removes lines that are, sometimes you have 2 lines overlapping each other, or some very small lines if you import or if you use different networks. But here usually it's already fine, because we have this algorithm in here that usually doesn't make these kind of weird geometries. But I'm wrong. So here you see the output lines are 203, and after this cleaning we have only 199, so there is a small difference. but I cannot see where these differences. Okay, with this you have a nice tool for a first draft of a street network. You can control a few parameters. That's a work in progress component. You cannot control the size of the blocks that are created. So far, you can do this in the next step, but so far you can only control the growth of the network itself and steer it based on these initial line segments or the border that you can move around. So it tries not to change it. It tries just to clean it, that you don't have any errors. This one removes here these dead-end streets from the network, because if we want to use these blocks later to create parcels, they are not considered because they don't form any meaningful block or something like this. That's why I removed them. That's a kind of network sketching tool. You can quickly change the boundary. If you just take the other one, then it's put into the circle and you can play around with it. It has the advantage that it generates the network immediately, but it has the disadvantage that it offers you only a limited amount of control, which you would have if you create your own definition or your own script. So that's the one I prepared. You can also use your own one. Just take care that it's not too big, because we want to use it for the simulation later. If you have an extremely large network, the simulation will become very slow in the next steps. Therefore, I use this smaller one. But it's created in the same way as I've just shown it to you. And you can control it here with these parameters. So that's our basic network that we want to use in the next step for this kind of network analysis that you know from Sven, where we compute the centrality measures in this network. So we want to use the street network and compute how central different street segments are. Therefore, what you need to do is to activate this. So I've just disabled this one to block the rest of the script. If you enable it, you should receive this one without any result. Here where you see the second red box, that's a new component, or I think you know it from Sven, but it's newly implemented. Maybe you are familiar with it. You have to check these output boxes in order to get an output. Unfortunately, it's unchecked always if you reload the script. This GPU, CPU, I mean, if you have issues, you can go to CPU, then it should work. At some computers, this GPU is faster, but it requires an NVIDIA compatible graphics card. And if you have something that doesn't work with this CUDA stuff, then it's probably not working. Then you have to switch to CPU, which is not a problem in our case, but if you have more complex analysis, it's faster with the GPU. That's this Floyd-Warshall algorithm that computes the shortest paths in a network. It computes it also for the street network, but you have to disable the preview in the beginning because this overlays the other streets. And then you see the result from this component here. That's what I forgot to say in the beginning. If you download the components and copy the folder into your libraries folder, you see here these 3 Alea folders. And if you get this error message that something is missing on your Rhino/systems folder, This is because we need to copy these 3 folders. Just copy them, so keep it also here, but copy it and go to your to see where Rhino is installed. Usually this is under C and programs or program files. And whatever, depends which Rhino you use. I use here Rhino 5. And then it's under systems, and here you see I've already copied the 3 folders into the systems folder. That's because for using the GPU, that's a little bit more tricky. We cannot just have it in the libraries folder. These 3 folders are needed in the systems folder as well. The box at the bottom, that's nothing else than the network analysis. What you do is you connect the network that we generated. So this is linked to our street network that we just created with this component. And then we link it as an input. Just switch to the first step, the process geometry. This creates the graph that will be analyzed. And then we have the second part, build the graph with custom length coefficients, or respectively with custom weights for using either the angular or the metrical distances. I hope you remember what this means. So angular just measures the angular turns between 2 locations. Metrical distances, the meters you have to go from A to B. And you can use your different weights. If I change it, then you see the analysis adapts as well, using different weights, either for the metrical or the angular weightings. Then this component is just responsible for computing the shortest paths. And this one returns you the outputs that you get from these shortest path computations. What I've done is I put here these weightings for origins and destinations into it. That's what we do with the rest, which I will explain in a minute, is that we link the parcels or these areas here to the street segments. And what I can do is that I say, okay, the bigger parcels have a higher impact on the number of trips that are generated, and also to the number of trips where you have the origin to. Therefore, I just plugged it in, but they don't have a huge effect because the areas are relatively similar in terms of the size. But you could do this, that you just reflect densities or potentials of areas. And what we receive here is the betweenness centrality, so how far away a street segment is from all the other street segments in average. The most red ones, or the red colors, the warm colors, represent the smaller distances. So in this example, from the center to all the other line segments, in average you have the shortest distance. And on the edges, of course, if you want to travel to all other segments, the distances are longer. What we use here is the length of the shortest path, which we need for the next step for our simulation. Maybe you remember it. This contains the length information of the shortest path between all line segments. So we compute the shortest path from here to here, from here to here, from this line segment to all other segments, and then from the next segment to all other segments. And here we return the matrix of these distances from all lines to all lines. That's basically this, the usage of this shortest path or the centrality computation. You can also get here the other measures, the in-betweenness, closeness centrality or the, where do we have it? So closeness centrality means how often you path a street segment if you travel from everywhere to everywhere, so it counts how often people pass through a location. This shortest path computation computes you the shortest path in the street graph, in the street network. What we do is that we take these areas between the streets, so the blocks that we create in this part of the script, create the blocks and parcels. This is primarily done with this street blocks component, which generates the blocks based on a street network. So you can put in every kind of network and you receive these polygons between your lines of the network. From there you can also subdivide these polygons into smaller areas with this parcels component. That's again from the decoding spaces toolkit, the street blocks and the parcels. And then you get the subdivisions for the smaller areas. You can have also more if you change this plot width parameter that controls the stop condition. At the moment it's 50. If you reduce it to 40, then you get more of these parcels. And this is very similar to what Malik introduced you, the generation of the individual parcels. In this case, for example, here you see we use a minimum bounding rectangle with the orientation of the longest edge of the minimum bounding rectangle and compute these parcels. The primarily condition is that we try to have a minimum width of the parcel at the street edge. So no subdivisions are generated if you don't have a street around it. Unfortunately, it still has some errors. So here you see these plots are too big. We are working on removing these difficulties. For some reason, they appear sometimes. But in general, you can create these patterns. So for the next steps, just make it not too detailed, because otherwise the simulation needs longer. Okay, so here you have then these parcels. And this part of the script is used to link the parcels to the nearest street segment, because for our simulation later on, we want to have the distances between these areas, between the parcels, the plots. Therefore, we look at the moment to which street this parcel is closest. So I just use the center point and look to which street this center point is at the closest, and then I link this parcel to the street segment. This is done in this part. We compute as well the areas for the plots for the parcels, and use these areas then as the weights as explained in before. And here you see these two visualization boxes. The one is for the street segments and the other one is for the parcels. They have now the same color as the closest street segment. So this red one is linked to this street, so that's a very central area, whereas this one is linked to this street segment, so therefore it's blue. This white, that's just a render issue. So here you see if you have this perspective, they are not white, they have also a blue color. It's just rendered white. From the center point, the distance to this line is obviously the shortest. I mean, it could have been also this one, but the algorithm decided to take this one. Of course, it's aligned to all the other lines as well. You could also decide or implement a different algorithm that decides to which street it is aligned. So you could also say, okay, take the, here it is already the longest edge, or you scan for the directly neighboring streets and align it to the most central one. It's difficult, but in this case, I decided just to take the nearest one. It's an approximation which you can make more detailed. But that's from where you get the information how central a plot parcel is. These parts of the components, they are used to link to get the values from our distance measures, because usually they are sorted in the same order as the street segments are sorted. And now we need to reorder them in order to find the right value from the street segment that we defined is in our case, the closest one. Now we want to know which value this street segment has and assign it to the plot. That's done with this item component, and then you just sort or take the values from the right indices of the street segments. This gives us our initial starting point. In the next step, if you remember last semester, we want to compute the attractivity of a location, which depends on the distance to the other locations, and having then a certain function, how important or how relevant this is to make my location more or less attractive. But we will look at this in the next step. What we get is this matrix that tells us the distance from all the line segments to all the other line segments. What we need is the distance from every plot, from every parcel to the other parcel. That's just looking for the right indices. So the indices we get from the part where we computed the closest street segment, so we know which segment is the closest, and now we need to somehow reduce the distance measures that gives us the values from all lines to all lines to the subset all areas to all areas, because the number of areas is smaller than the number of lines in this system. That's done with this C# script. So you see the order that we get is from line segment 0 to line segment 0, from line segment 0 to line segment 1. These are these indices, and there are many, 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 from line segment 14 to 82. These are our indices that gives us the values which are the distances. And from these values in the C# script, we look for the ones that indices, we have the list of indices that we are interested in. So these are our indexes that we want to know from which to which, what kind of distance do we have there. Here you see the usage of a data tree in a script. That's always very special. You have the distance tree, this one that we looked into here. That's the tree that we have, and we want to create a new tree that corresponds to the areas, the distance matrix from the areas to the areas. To take a path out of the data tree, so the data tree, if you remember, it looks like too many entries, cannot see it. Maybe you remember the visualization from Martin before there, it looked much better, maybe the smaller one. Yeah, here. So the data tree, so these are the branches, and in the dots are the values. In the end, it's a kind of a list of lists, and the dots holds the values of this tree. And what we do is this GH path, that's one of the lines, one of the branches in our tree. It can have more steps, therefore it's a path, not only a branch. But we take this path, we generate it. You generate this array. An array is very similar to a list. This syntax with these two brackets means that's an array of integers, which looks very similar than a list. And you put in two values, and these are the indexes from where to where. These are the indexes of our street segments that corresponds to the areas, to the parcels that we want to connect. And this is our new path. So we use this V array to generate a new path, this V path, and this tells us the indexes. For example, if our area is the area 14 and we want to know the distance to the, if the area is connected to street segment with the index 14 and we want to know the distance to the area that is connected with the index 82, then these would be the two numbers that we would have here in this array. And from this array, we create the path. And we take this path to get the right distance out of the distance tree that we have put into our component. That's the path to define where to look for the correct distance between these two locations. And then we add this distance to the new path that we created, which is just the first one that we are looking for. And the new matrix has just the same order, or our output is ordered in a way that we have the distance in the same order as the areas, as we have had the areas. At the moment, they are ordered corresponding to the street segments. What we need is the order corresponding to the areas. That's what's done in this script. And here we generate a new branch, so this is the new path that we add to this distance tree, and this distance tree is the tree that we return. This is then returned here. So the whole component is just resorting the distance values from the sorting of the street networks, the lines, to the distances between the areas. Probably there is also a way to do it with existing Grasshopper components, but I haven't figured out how to do this with the components. What you receive is this new tree with a reduced number of entries. These dots corresponds to the number of areas that we have. What we receive here is a list of indexes that correspond to the segments that are linked to areas. And what this script is doing, it takes, for example, this 78, the index 78, which is also in the distance matrix or this distance tree for our network. And then we look for street segment 78, maybe this one. And now we want to know to which other segments or the distances to all the other all the other areas, which are the remaining numbers, everything except index 78. That's the distance from this area to the other areas. Or these are the distances that we want to know. So this means we take out here all distances from index number 78 to, in the next, for example, 78 to 42. This would be the path that we generate, 78 to 42. We look in this list for this entry, take it and create a new branch for this tree. That's our first branch of the new tree, which tells us distance from here to there, for example. And then we do this for the next, from here, we do this from here to there, from this one to all the others, and then we go to the next. We have had this information for the streets. What we do is we reduce this, or we just take the information that we need for the areas. The two areas choose the same segment where they are assigned to. Yes, could be, for example, they are probably taking both this segment. Means there is no distance between both of them, which is okay because they are at the same street segment. They are neighboring to each other. There will be street segments that have no area.
But that's not what happens to the white areas on the map.
No, because they are not white. They have a color. They are just visualized white. That's. And because the street segments, so the number of street segments is different from the number of areas and sorted differently, that's exactly why we need to do this reassignment of values, of distance values to the areas. But I mean, in general, if you want to assign areas to street segments, you can just reuse this. You don't need to understand the details. What you need to understand is then the logic of the simulation. You know it already. If we activate this data component or enable it, then the information is sent to the other script components. Maybe you remember last semester we have used this grid city that we have also used for an exercise. Now we just replace the grid with this more precise information concerning the distances between locations. And if you run now this simulation, so that's this anemone loop, if you double click, in order to see the result of the simulation, you should turn off the preview of the centrality values from these green boxes and turn on, that's already turned on. And if you rerun it, then you see this typical development where we distribute new people in this kind of abstract city. So in this cloud-like part of the script, we have here this anemone loop or the loop component. You may remember the logic. We have population and workplaces in this city. And we start with an initial setup, which we can control if we turn it off and restart it. So the first person is located somewhere here. We can control this by placing a point and linking the point to this input geometry of our C# initial component. And if you move this around, you can control where the first person in your city is placed. Or I mean, it's placed closest to this initial point here. You can see this if you open this C# script. There we just define where we place the first person what we do is we compute the minimum distance between this reference point or we compute the distance between the reference point to all our areas, and then we just look for the smallest distance, and that's in this case this area where we remember the index, the reference index, and this reference index is used for our list where we store the population distribution, and there we just say, okay, here we have 1 and in all the other places it's 0. The first workplace is just placed at the first index, which is somewhere randomly. Is it clear how the initial initialization works? Okay. You can also manipulate it. You can have more initial points. The next step, maybe you remember this as well, computes now the attractivity. Means how attractive a location is for somebody who enters the city in the next step. We can also visualize it. So that's the current attractivity map, and this is based on the script that we have in here. So if we look into it, what we do here, so this for testing is not necessary. The more important part is where we compute the attractiveness of a location. And we do this, we use our distance tree and look for the distance between all the different areas. So we take this distance out of our tree. So we compare here, we want to know the distance between place K and place I. We have here these nested for loops. And this distance is used for the computation how I perceive things in a certain distance. So this is a kind of perception parameter, and I defined here that it decreases exponentially, means the farther away things are, the less important they are for me. This is this distance perception of the population. I also defined that if it's farther away than a certain number, it just cut it. You don't need to do this. And now this was the perception, how I perceive things in a certain distance. Now I need to decide if what I see is something that I like or what I don't like. In this case, we define that this distance perception to, for example, if I see other people, means my initial number here is 1, and if I am at this place, I take this number of people in this cell and multiply it by the distance, respectively by my distance perception. And this tells me how attractive this cell is for me, which I consider currently. For a new cell, I compute all the distances, or I use our distance tree to all the other distance and multiply it by the existing population in these cells. That's then the current attractivity. This, what's visualized here, is now the attractivity map. So before I have had the distribution of functions. What we link here is now the visualization of the current attractiveness of locations. So this means the more red they are, the more attractive they are for new population that moves into the city. That's our initial condition or initial state of the system. If I move the first person here, and the rule is that locations are more attractive the closer they are to people, then the image changes for the attractivity map. Blue means not attractive. If you remember, in the exercise last semester, we used this grid city, and there the distance between the grid cells were just the x and y distance, so the Manhattan distance in the grid. This is, we just replaced this distance by the distance of this irregular grid. Computed a little bit more difficult using these components, but in the very end, if you want to do this, you just need to plug in your network in the beginning and take out the distance matrix at the end. So you could also consider this as a kind of a black box. If you want to reuse it, you just need to know how to use the input and output values. More important is that you understand the logic of these attractivity functions, because these are things that you can manipulate. And here, that's also the link to what we've seen in the model from Martin, for example. When you use the logic from this von Thünen model, this gives you a different function to compute what location is attractive for a certain function. Here I have assumed something very, very simple, just the nearness to other people or the nearness to other workplaces. But the workplaces, for example, they could have a much more complicated function that have to do also with distances to marketplaces, as we have had it in the von Thünen model, and also the rent that you can get at a certain location. So you can combine these logics in your model just by looking into the function and exchanging parts of it. So we have distances. I mean, that's just a different view on a very similar thing that Martin has done in a different way. So he computed also distances from grid cells to streets. Here we use distances from areas to areas. But in the end, the logic is that near things are more important for me than things that are farther away. And these distance measures, these are the most important aspects also in these von Thünen models, and in probably all geographic models, distance is the key factor. Then the decision-making process, how a new person who enters the city decides where he wants to be located. Therefore, we use this so-called roulette wheel. You see this down here. So now we have these attractiveness values. And if a person enters the city, he or she wants to go to the most attractive location, but we don't use always the most attractive one. We make a kind of random selection, but not completely random. We use this roulette wheel selection that you say, okay, areas with a higher attractiveness, these are bigger slots, and areas with a smaller attractiveness, these are smaller slots. And now I generate a random value, like rolling the ball in the roulette wheel, and the probability that this value falls into the bigger slot is higher than it falls in a smaller slot. Therefore, the selection process uses these attractiveness values, but adds a certain amount of randomness. We do this for the population and for the workplaces. The workplaces has a corresponding logic. Attractiveness for workplaces looks similar, and the decision making is also similar. We do this 10 times for workers and 10 times for new people. And with this, if we visualize the outcome instead of the attractiveness, if we run it now, we can observe the density distribution in our city. In this case, we look at, what do we see? The distribution of the people. Red colors are higher distribution. Also, if we move this initial place, the simulation will develop differently. What is added now, there is the third part, which we can use to have a kind of simulation how the system will develop over time. So of course we can make a planning for what happens if 10,000 people enters the city in one moment of time, but we could also introduce this stepwise growth. Therefore, the idea was, or I mean it's one concept, that we filter the areas that have a certain density. So here you remember we distribute so and so many people per step, and we say if the density is higher, in this case like 5, for example 5 or 2 workplaces and 3 people living in a cell or occupying a cell, then we consider the cell as developed. Means we build something on it. In the end, the potential would be high enough to develop this area. If you turn on this poly offset component, oops, not preview, then what you can see is we activate the rest of this code. We create again another step. We create parcels inside the parcels, assuming that these are secondary and primarily streets. So the street network that we have had could be the primary network with the main streets, and now we create a secondary street network. This is then in between these or in between the areas that we used before. And they are subdivided again using this parcel component, having a plot width of 20. If you decrease the number, you will generate more plots. And if you run this simulation again, you see this happens only at locations with a certain density. So here you see this is occupying these areas step by step. These are still empty because the potential to develop them is not high enough. We can continue with these components to add also buildings. So we have implemented a few basic building typologies. Therefore, we need to activate these buildable areas. Here you can restrict the areas where it's allowed to build. For example, here you have these setbacks. You have a certain setback from the street and from the left and right neighbor, and from the backside of your plot you can define different setbacks. So if we change this value from 3 to 5, you see the setbacks increased to the neighbors to your back. To the street, it's smaller. And these buildable areas you can use for the last component where we generate the buildings itself. This doesn't matter, you can use also another one, offset. There is this offset component which is doing primarily the same job. Distance 3 and curves. You just have to use your negative values. So if you want to have an offset, it offsets it with positive values. Sorry. And we want to have negative values. Therefore, what you can do is to right-click on this distance value and go to expression and say minus x, and then it it multiplies it by -1, and then you reduce them. And you can then just use this one, put it into the following one, and then you can replace the poly offset component, which may not work. So this offset component, that's an existing grasshopper component. It may be not that precise, but it should work as well. So here you get also, or you reduce the threshold to 0, then you may also have an output. Okay, looking into the last part. So you define the buildable areas. These are the green polygons. So this is, these are generated by these different offsets from the streets and from the left and right neighbors and from the back side. We can take now these buildable areas, the plots, to the buildings component and enable it. And this generates us then a certain building typology into the generated areas. And so there are at the moment we have 3 predefined typologies: these freestanding buildings and the block. There is also a control parameter that allows you to control the density that you use for these plots, these FRA values. If we reduce this, the building height decreases. You can also change the manipulation, the orientation. Then the buildings don't orient themselves to the boundary areas, but they will rotate to a certain direction. Of course, there's also building depth. And what you can do here in general is that you relate these parameters to some other values. For example, to the outcomes of our simulation. If we have more population at a certain area, we can say, okay, the building depth can be bigger, or the density value can be higher, means we can build more because the pressure to this area is higher. Or if it's somewhere at the edge, we can say it's smaller. Or if you have a different usage, you can change the rules how these blocks can be filled. Some places it's a bit weird. So that's a starting point for you to link the different parameters of various kinds of models to geometries. And I think here we can also link this in general to the simulation. If we run the simulation again, it occupies these areas step by step, depending on which one is developed. You can do this, of course, also with the logic that Martin introduced, or you implement your own logic. But this is the basis for the next step of your planning project this semester, that you make a concept what aspects are important in terms of thinking about these metabolism ideas, what you want to include your model, which aspects affect the geometry or other parameters. And then we have to discuss how you can link this to this basic setup that we provided to you, or you come up with your own one. This is thought just as a starting point for you, that you can use something to start with to make first sketches for settlements, how this could work, how it could look like, or you dive into some definitions and define something on your own, some rules, how structures like these may develop. That's up to you. The idea of these models that we provide you is really just to give you ideas how this logic can work. You don't have to work with the Thünen model. It's just an example. If you decide to use an economic model, you can implement it like the Thünen model. You can change parts of this model, have different economic logics, different aspects that may play a role in the model, not the soil, not the rent, not the market price, something different. But the logic of the model can easily be adapted. Or it can be adapted, maybe not easily, but you should know how you model it. This was the idea of introducing these models today, and also at the last meeting 2 weeks ago with the distribution of the cities. But especially today, this should give you a starting point how you can put things together. And I would recommend that before you work with the code and these components, that you make a sketch and some concept drawings, what elements are important, to which theoretical concepts to refer to, are there some social aspects or some spatial things that are important, some open space aspects, or something that's more important for pedestrian comfort or for economic aspects. Many things can be considered. We will need some kind of economic logic because to develop a new city, you need to provide workplaces. That's the key driver for attracting people. Otherwise, they will just migrate to another city, to another place. Therefore, we need to have an idea how this system can work, how it can develop, how it can sustain itself. You could also include aspects on somehow energy production, looking into the data that we get from this Euroscape model. These are just starting points. We are finished. Thank you for being here all day, and see you in a month.